All right, you've had a couple minutes here to work on this one. Let's see what you came up with. For this ln of xy, how many of you did the product rule? Okay.
I did both ways.
You did both ways? Okay. You could do the product rule. All right. Or, what did the rest of you guys do? Yeah, there's multiplication inside, so you could rewrite it as ln of x plus ln of y. Either way, it'll work. Okay? Real quickly, since most of you didn't do it this way, if you had done this using the product rule, it would have been, this is going to be over xy, because it's the derivative of the inside over the inside. So derivative of x is 1 times y plus the first times the derivative of the second, so that xy prime. Okay? And then that would be plus 5 equals 0. Then you do some algebra, you subtract 5 and multiply by xy, and you get a negative 5xy equals y plus xy prime. And then you subtract the y and divide by everything by x, and you get a negative 5xy minus y all over x. Okay? Now, if you did it the other way, you had ln of x plus ln of y plus 5x equals 30. And then what you did is you had 1 over x plus y prime over y plus 5 equals 0. Right? So then you subtracted the 5, you subtracted the 1 over x. So you had a minus 5 minus 1 over x equals y prime over y. And then you multiply both sides by y, and you get y prime equals a negative 5y minus y over x. And if you look closely here, you'll notice that if I were to multiply this by x over x and get a common denominator, I'd get the same thing. Okay? So these are equivalent. They just look slightly different. Okay? But they're both right. Okay? And that's what's kind of nice about these guys, is you have more than one option. So which option should you choose? Whichever one you happen to notice. Okay? Whatever one you want. If you notice that it could be done both ways, just pick one and go with it. All right? Now, the second example here, some of you may have gotten started on this one while you were waiting, but the second example here actually is one that we could just take the derivative of explicitly, because it's the explicit definition of y in terms of x, and we would get a result in terms of x. Okay? However, this actually asks us to take the natural log of both sides of the equation, and what we'll do is we'll actually find y prime in slightly a different form using implicit differentiation. And it actually is kind of nice here because, notice, here after we take the natural log of both sides, I could take the derivative, or I could rewrite, this as 2 ln of x minus 2 minus 1/2 ln of x squared plus 1. So you'll notice here, I rewrote it with the division becoming subtraction, and then I took the square out as a coefficient of 2, and I took the square root out as a coefficient of 1/2. All right? So here is a case where we can use the laws of logarithms, and this actually makes things kind of nice, all right? Because now, when we take the derivative of both sides, it's really not too big of a deal, okay? I take the derivative of ln of y, and what's that? 1 over y dy dx, or 1 over y prime, okay? 1 over y dy dx. When I take the derivative of the right-hand side, notice it's just 2 times the derivative of x minus 2 is 1 over x minus 2 minus a half times the derivative of x squared plus 1 is 2x over x squared plus 1. Okay? I can cancel out the 1/2 with the 2 here. But notice here, to solve for dy dx, all I have to do is multiply both sides by y. And my final answer would be dy dx equals 2 over x minus 2, I should say 2y over x minus 2, minus xy over x squared plus 1. Okay? Now, could I say that that is f prime of x? No. Because f prime of x is an explicit definition in terms of x only. This has y's in it. So I can't say that. But this is the derivative. And I can plug in a value of x and y and figure out what the slope of the tangent line at any point is. Okay? And that's maybe a little bit easier than doing the quotient rule along with the chain rule. Okay? So, that's a little bit of a warm-up here for our lesson today. What I want to look at here, though, is kind of address an assumption we've kind of been making the whole time, and that is when we have been taking the derivative of natural log of x, we've been assuming that we hold to the domain. Okay? We would say that that's 1 over x, but we recognize that the domain of the natural log is what? What can x equal? Anything bigger than 0, okay? So this is for x greater than 0. Okay? Now, our theorem that we're looking at here actually allows us to address functions, those u's, that do go into the negatives, okay? And we do that by taking the absolute value, okay? So here, the derivative of the natural log of the absolute value of a function is u prime over u, okay? So we've kind of just been assuming that it's always greater than 0, but now we're actually, with the absolute value, it kind of forces the value to be greater than 0. Okay? Now, that doesn't mean that there won't be points where the derivative is undefined. For example, anywhere that u equaled 0, the derivative would be undefined. Okay? Because you can't take the natural log of 0. And notice, if I'm doing u prime over u, then if u is 0, the whole thing is undefined. Okay? So, three quick applications of this. First of all, if f of x is ln of the absolute value of cosine, then f prime of x would be what? It would be, what's the derivative of cosine? Negative sign.
It's like absolute value.
Well, true, but it's still, notice it still says u prime. It doesn't say the absolute value of u prime. It's the absolute value of what's in the natural log. So it is negative sign over cosine. And I heard someone say tangent. You're right, that's a negative tangent of x.
But what's the point of putting an absolute
Yeah, isn't it like the same thing?
It's very similar, except here we're actually able to deal with values that go into the negatives because the absolute value pushes them back up into the positives. Okay? When we were doing these back here, we were only allowed to look at the values where x was less than 0. Okay? Now we can look at negative values of x as well.
It doesn't change anything in terms of solving.
No, it really doesn't.
So like if that says L, the derivative of ln absolute value of x, it would still be 1 over x?
The derivative of ln of absolute value of x,
Yeah.
it would still be 1 over x, but you would not have, the only real number that it couldn't be would be x not equal to 0. Okay? Because the derivative is undefined at 0. But that's because the derivative is undefined as well. Here, it had to be greater than 0, even though negative numbers would have worked in 1 over x. But when I have the absolute value here, I'm allowed to include the negative numbers. Okay? So that's where it's different. It's not different in how you're taking the derivative. It's different in what values of x that derivative will now apply to.
It changes the domain.
It basically, yeah, it changes your domain.
But if I put in my calculator 1 over x, like it's going to graph the same thing for both of those functions.
Yes, it will.
So I have to know that if it's an absolute value function, not to include.
Well, if it's an absolute value, then what you graph is what you get. If it's not an absolute value function, you've got to consider the domain of the natural log first. Yeah. Okay. All right. Now here's another one. This is a good application and reminder. Okay. Show that y equals x times ln of x minus 4 over x is a solution of the differential equation x plus y minus xy prime equals 0. Okay? Now, there are a few different ways that you could handle this problem. Alright? I could plug in x ln of x minus 4x in for y right here. And then solve. Alright? That's one possibility. Another possibility would be to actually take the derivative here. Okay, and also solve for y prime over here. So for example, if I subtract x and subtract y, that's a negative xy prime. And then if I derive, I'd get y, or if I divide, I'd get y equals a positive 1 plus y over x. Okay? Well, if I do the derivative over here, y prime is, I've got to do the product rule, right? X times ln of x. So that's going to be x times the derivative of ln of x, so that's x times 1 over x, plus 1 times ln of x. Oh. ln of x minus 4. Okay, and you're like, well, that doesn't look really a whole lot like it. Okay, well, let's keep going. This cancels to 1. So I have a 1 minus 4, which means I have an ln of x minus 3. Okay? Well, if I go back over here, remember y equals x ln of x minus 4x. Well, I can substitute that in for y here. And watch what happens. Y prime is 1 plus x ln of x minus 4x over x.
Wait. You substituted, but isn't that, oh, sorry.
Okay. And then, of course, this x and this x are a common factor of the numerator, so I can cancel that out with the x on the bottom. And look at what I've got. I've got y prime equals 1 plus ln of x minus 4, which is ln of x minus 3, which is what we were looking for. Okay? So that's another application. And again, there are multiple ways you could have done this. I could have plugged that in for y at the beginning and showed that it came out to y prime equals 0. Okay? Either way works. Okay? Last one here. Locate the relative extrema. Alright, when you hear relative extrema, you think bad memories. Critical values, yes. Get the derivative, set it equal to 0. Okay? So we're going to do y prime equals the derivative here. So that's the derivative of the inside, 2x plus 2, over the inside, x squared plus 2x plus 3. Okay? So, to get critical values, what do we have to do? Set it equal to 0. Alright? So, equals 0. Notice the denominator does not factor out at all. Okay, if it were a minus 3, or if the 3 and 2 are switched, it would factor, but this one doesn't factor. So, because remember, when you're looking for critical values, you got to consider where it equals 0 and also where it's undefined. In this case, we only get a value where it equals 0, and that's where x is what? Negative 1. Okay? So if we were to make a sign diagram, and I plugged in 0 for x, all I would get is 2 over 3, which is positive. So I know that at 0 over here, it's positive, which means my function is increasing. Okay? To the left, if I plug in a negative 2, the numerator would be negative 4 plus 2, so that'd be negative. The denominator would be 4 minus 4 plus 3, which is positive. Negative divided by positive is positive. There's negative. Yeah. Alright? So, we're decreasing here, we're increasing here, so by what theorem, or by what rule is negative 1 a min? The first derivative test. By the first derivative test, we know that there's a minimum point at negative 1. Okay? So there's a min at negative 1, and then to figure out the y coordinate, you plug it in. Negative 1 squared is 1, minus 2 is negative 1, plus 3 is 2, so we have ln of 2. And if you were paying attention or looked over here, you'd see that that's what the answer was supposed to be. Okay? Relative minimum at negative 1, ln of 2. And by the way, don't plug that into the calculator. Don't bother. Just leave it as the exact value. Same thing like with things with pi or stuff like that. Okay? So, just a couple of applications of what we're looking at here. It's not terribly difficult, okay? But it does take some practice. You do need to work through some of these and make sure that you know what you're doing well and can work efficiently on these.